Okay, hi, I'm Jaka, and today I'll be talking about trust in machine learning. Or to be more specific, we'll focus on post-processing, an often overlooked step, so I hope this talk does it a bit of justice. We'll take a look into explanation of predictions and models as a whole. Explanation in this context means a formal procedure on how to make sense of a prediction. Or, in other words, how to scientifically justify your predictions to your boss or to a domain expert who probably isn't a data mining specialist. So let's first review what do we actually do with the data. We'll assume we have a classification problem, so we have a nice tabular data set of examples which are described with attributes, and we'd like to train a classifier on this to predict a certain property. So, for example, we could have a database of mushrooms and their descriptions, and we'd like to figure out for a new specimen whether is it edible or not. To do things right, we should approach this through a series of steps. Now, first comes the exciting bit where we find the data set and we basically figure out what we want to do with it. How will machine learning help us? Then we pre-process the data. This means we remove the noise, we figure out if there's any anomalies in the data, or if are there any missing values or conflicting values, and basically make sure that the data is clean and valid. Now, this can be very tedious, but it's also very beneficial. Similar to this is transformation. Now we have to normalize the data, maybe change continuous attributes into discrete, and basically make sure that it's ready as an input to our data mining procedure, the cool bit. Now here, we basically fiddle with the parameters, tune the algorithm to get our awesome prediction, and basically here's where the interesting stuff happens, which is very good. But aside from evaluation of performance to satisfy our levels that we wish to achieve, we basically often skimp on post-processing. What we want to do here is change these models and predictions into knowledge that would provide the most value to our user who probably isn't a data mining specialist. Now, certain parallels with pre-processing are very clear here. So both are processes that aim to achieve clarity and reduce noise. But with pre-processing, we do this on the input data set. But with post-processing, we do this on the output data set, in other words, on our predictions. Now, this could mean various types of evaluations of performance, the most common type, or maybe we integrate different sources of knowledge, or maybe we want to filter or prune the model so we make it smaller and more coherent. And also, we often plot the data. Now, time and time again, it has been proven that basically showing the data is one of the most efficient ways of presenting the results, since human beings are very visually oriented creatures. Then we come to explanation. Sometimes, even though a prediction is very good, so we know it's very accurate, we want to have it explained. So we want to know, how did the classifier came to its conclusions? What factors influenced it? This is because, in general, machine learning exhibits a black box nature. That means we don't know exactly what classifiers think about when they are, running our CPU cycles. So the connection between input and output is not clear, which is quite honestly, most commonly, very good for us. I mean, the algorithms simply work. We just chuck in the data and that's it. But on the other hand, we hinder the usefulness of the predictions since they are more difficult for us to trust them. Now, trust is the key issue here. The lack of trust can have a very high impact in environments where a high level of human oversight is necessary, or maybe where the predictions can be very costly, such as in the medicine field. So the model has to be transparent. For example, if a 95% accurate algorithm were to predict that an open surgery should be performed upon you, you'd probably want to have an explanation why, or at least you want to have your doctor to know why. So, in other words, the predictions in the models must be easily understandable, which is already the case sometimes. As you see here, with decision trees, we basically just prune them, plot them, And then we follow the attributes through the decision nodes, arrive at the leaf level, and we have our class. Or similarly with naive Bayes, naive Bayes can be very easily made understandable through the notion of odds. Both of these examples were run on a famous Titanic dataset, and for example, we could clearly see that being an adult male in third class was not a good position to be at on Titanic. Now, to figure this out, we don't have to be data scientists. We just have to simply read the charts. But in other cases, things are not so easy. Well, what if you have a support vector machine in a large dimension? Or how do you figure out how do random forests come to their conclusion through voting? Or maybe peek inside a neural network? Granted, these models will probably achieve very good predictions, but we're kind of just expected to believe them without any additional justifications. Yes, and the smart people at the Faculty of Computer and Information Science in Ljubljana realized this and devised a generalized method of explanation suitable for an arbitrary classifier. Basically, this explanation methodology is a homegrown product. So it enables us to explain predictions and models as a whole through the notion of contribution. A contribution of an attribute value is basically a measure of how much influence did the attribute have on a final decision, be it either positive or negative. This method handles noise or redundant attributes, or even finds out any interactions between attributes. So the figure on the right is an example output. Here again, we're explaining the Titanic data set. To be more precise, this was a k-nearest neighbor. So a simple classifier run out of the Titanic data set. We want to figure out who survived. Now, you might say that this is nothing special, as we've done the same thing 2 slides back. But we have to realize that this can be run on an arbitrary classifier, even on the scary ones from before. So not only does this method enables us to compare classifiers in a completely new light, not only relying on performance, such as most usually accuracy. Here we can actually see inside of the decision procedure and maybe consult with a domain expert whether these concepts actually make any sense. And the domain experts themselves can then figure out any additional knowledge that the classifier learned and basically reinforce their trust into the procedure. Now, this very method was already applied at the Institute of Oncology in Ljubljana. So basically, the problem was the prediction of breast cancer recurrence in the next 5 years. So will it reoccur in the 5 years or not? The guys from the faculty trained a random forest on the data and achieved a 73% accuracy, which is actually slightly above the level of oncologists themselves. What's more remarkable, though, is that they achieved a 94% agreement rate when consulting with the oncologist on the topic of explanations, or basically when they explained the model itself using this method. In other words, the knowledge from the classifier was in agreement with the medical knowledge, which is exactly what post-processing methods aim to achieve in exactly how they reinforce trust in machine learning. So at our last meetup, Rok used a great data set describing a bank marketing campaign in a Portuguese bank, which is basically a database of bank clients, so their age, income, marital status, and so on, and their previous interactions with the bank, so successes of previous campaigns, and some socioeconomic indices such as Euribor or employment rate and such. So our goal was to predict whether a client, when called, will deposit some money. So in other words, is it worth it for our marketing department to call them? Now, we've already established that, yes, this is very possible to solve. I mean, if you use machine learning, we can have some useful insights. But now we'd like to explain this. So we did the basic pre-processing, so discreditation of data. We removed the duration of the call attribute since it influenced the final decision too much, and trained several classifiers. The best were support vector machines, neural networks, and random forest. The next example I'll show on the random forests, but we'll address the comparison of the models later on. So, our random forest says that this particular 30-year-old university-educated administration worker who is single will deposit some money. Now, what makes him think that? This graph represents basically the most important factors according to the forest. It's interesting, so we see that the most important thing was previous contact of the bank to the customers. So we see that from the variable P days that the customer was contacted relatively recently, and the outcome of the contact was a success. So the client did deposit some money the last time that they called him, which is quite interesting. That means that the random forest really values customer loyalty in a sense. And one would expect that the next important factors would be related to the person himself, so maybe income or if he has a job, but random forest thinks otherwise. So socioeconomic factors come next. So the employment rate, the Euribor, and also consumer confidence index. All in all, it seems that the random forest thinks that the previous successes with the client combined with bad economic circumstances makes people stash their money away. Now, what about neural network? How does it think? Well, the answer is quite similarly to the random forest. So they're both really keen on customer loyalty and socioeconomic factors. But there are some differences regarding timing. Random forest seems to put some emphasis on certain autumn months. I'm not a bank marketing expert, so I don't know if that makes sense. While the neural network seems to really dislike Mondays and Fridays. So the client should be contacted in the middle of the week, I guess. And also by cell phone. Neural networks dislike stationary telephones.
How do you know that these two are alike? Because they don't look like they look very different.
Yes, the visualization is quite squished here. But basically, the most important attribute values are the same. So previous outcome and previous time of contact. Yes, but there are variations in socioeconomic factors, but basically the grim circumstances in the country increase the likelihood of bank deposits. Now, I have another one, a bit more a music example from the mushrooms that I introduced at the beginning. So basically, we have the descriptions of mushrooms from Agaricus and Lepiota family, and we want to figure out whether a specimen is edible. Now, I hope I don't have to emphasize that you should not rely on machine learning when deciding which mushroom you should put in a pen. But on the other hand, we're curious and but we're curious and we want to figure out if the algorithms are accurate, or maybe even better yet, if we can explain them and consult with a real mushroom specialist whether this concept makes any sense. So, it turns out that the neural network finds almond-smelling browned mushrooms with crowded gill spacing quite tasty. Now again, we achieved a very high accuracy here, but only after this explanation we can basically begin the discussion whether this makes any sense. So I don't know if this makes any sense, since I'm not an expert. But if I ever find myself talking to a mushroom expert, I'll have some real hard data to present to him and basically have a nice discussion based on that. Now a word of warning. This is not a magic pill or a crystal ball. We must always keep in mind that we are explaining the model, but not necessarily the knowledge behind the data. So only if the model is good at what it does, that is modeling the data, only then we can basically get some value from it, or basically take the concepts from the model as the concepts from behind the data, from behind the data domain. So if our model is rubbish, the explanation won't make any sense. What's worse, if we don't realize this, that the model is rubbish, we can falsely trust the explanation, which goes right against the goals of post-processing. We'd be better off knowing nothing. So we have to be careful here. This works good on good models. The correlation is basically linear. the other thing to be concerned about is the number of attributes that we have. Now, even from the example before, there were quite a lot. This is a twofold problem. Basically, the method can be quite computationally expensive, and if we plot too many attributes, the explanation is made, basically, the explanation is not understandable, which again goes against our goals. So there you have another reason more to pre-process your data. Now, briefly, how does it work? For detailed and rigorous descriptions, see the articles listed before, but it's a really neat solution, so I'd like you to have at least a basic idea about it. And that basic idea is game theory. So we have a cake or a prize, which is, in our case, the prediction difference. This is the difference between the prior class probabilities and the probabilities that we get after we apply machine learning. So, in a kind of sense, it's a measure of knowledge obtained. Then we have the players, which are, in our case, attribute values. And the players in this kind of game want to split the cake, split the prize amongst themselves in some fair way. And in some fair way, in our case, means that the more important attributes should get a bigger slice of the cake. In other words, we just described contributions. So a lot of math later, we get the graphs that we've seen before. So the gist of it is we use game theory to divide the knowledge of machine learning amongst the attribute responsible for it. Now, what else can we do with this? Well, we can use the idea in data stream mining. Since it gives us insight into the inner working of the models, we can use it for change detection. The fundamental problem in data stream mining is the issue of change. So our model in a changing environment can soon become obsolete, and we have to adjust it to the new circumstances. And detecting this change can be very tricky. At the very latest, we figure out something is wrong when our error rate goes up. But instead of just watching the error rate, we can watch the inside of the model and detect the changes based on the inside working of the model. This also means that we have insight into what attributes are responsible for the change. Or again, if the model is good, what changed in the environment that caused the concept drift, we call it. This is a work in progress for my thesis, so as always, the results are encouraging but not yet conclusive. So, I hope that I somehow managed to pitch post-processing to you, that you remember it the next time you're wrangling some data. As you've seen in the examples, it really doesn't take much to shed some light on the predictions. And this can save us some time, or maybe even reduces the likelihood of us getting food poisoning. In any case, even though a magician does not reveal his tricks, in the case of data science magic, you really should make your users understand the predictions and the models, as we rely on them more and more, and sometimes in the areas which are influential to our health. Thank you. Yeah. Sorry. Yeah.
How can we use it without coding it all up by the research paper? So is there already something that we can take and use in languages like R, Python? For
yes,
example, and two questions at once, okay, if I may. So, how computationally expensive is it? So if I have trained a classifier, right, do I have to rerun it, or what does happen?
Yes, it's a good question. So basically I said the computation was expensive. This is because to achieve a 100% accurate explanation, we'd have to basically run the classifier through the power set. So we'd have to see the combinations of every attribute and how does the classifier classify them. So in that way, we can figure out redundant attributes and the interconnections between attributes. So we don't do this when I said a lot of math later, at the game theory slide, there happens the approximation math. So we can basically tune the sampling rate in order to the percentage of accuracy that we want to achieve with the explanation. Oh, I believe the first question was about the existing implementations. Yeah, I'm aware of two. One of them was written in R, and the other one was written in Python by me. So I'm not sure if there are any else, but the paper is really good. Implementing it. My package? No. No, the package is in my thesis currently, so I have to graduate. I mean, the paper is really clear. Figuring out the algorithm, I mean, implementing the algorithm really is not a big thing. Yes.
It seems that when attributes are independent, this makes perfect sense. But
yes.
How does it actually deal with attributes that are not independent?
Well, this is basically more the issue of presentation than the method itself. The graph that we've seen here, where yes, we're all independent, you know, all the values, but actually the method outputs the combination for each attribute. Now, I mean, for each combination of attributes, I just plotted here the most important ones. So it is a problem if we get, you know, two attributes that are connected, how to present this. And this is more of a visualization problem. I mean, if we don't bother, we could just, you know, list them in a table, which is actually a very nice solution. But so the method handles them, but plotting them is difficult. Yes. Yes. It works on binary class, but we can convert multiple classes into a binary class problem with various techniques exist. So, but it works only on classifier currently, so not on regressions.
All right, maybe slightly more philosophical question.
Okay.
How can we trust your method? Because when I see it, to explain the black box, we put another black box on the top of the black box.
Yeah, this black box is a lot more transparent, but I blacked it when I said a lot of math later. So basically, this method is, the articles actually contain proofs for your very question, but they really aren't suitable for slides, I'd say. But yeah, it's a rigorous procedure.
Is there another question? So just maybe in connection to this not independent. Thank you. So connection with not independent parameters. So if you have two attributes that are connected,
yeah,
and if both are set to some values, you have really high score, or you have positive class, whatever. So what then? Will the both parameters will be like, both attributes will be kind of highly ranked in this method, or just one of them, or?
The pair of them.
The pair of them.
Yes, because if they actually act in pair, you know.
Okay.
I don't know how. If we have a condition that we only go out if it's sunny and warm, yeah, then only the combination will have a high contribution, you know, because.
But then interpretation could be wrong. Then if I just kind of use different value for one of them, actually both would fall off the chart of importance.
No, I mean, I plotted here only the singletons, so no interactions were actually plotted because they weren't found.
Ah, okay. You have a pair plotted together.
Yeah, you can. Yeah,
okay.
Basically,
okay.
Again, it's an issue of presentation.
Okay.
Now, another thing that's important here: our classifier must be able to handle interactions. So, if our classifier is dumb, we won't find any interactions in the model. Yes.
First to say, I also very like the work of Strumbel. I mean, this was an excellent thesis at our faculty, but I think I gave him the same question 5 years ago as now. So if you have a black box, right, and you replace it with a graph of explanations like you did, right?
Yeah.
And these are all linear combinations, basically. I mean, you could easily then say, okay, this graph actually are like beta values for logistic regression. So if this is true, right? You don't need a black box anymore, but logistic regression would work perfectly.
But you can put any classifier under this.
Right.
Yeah.
But if you can draw the graph, right, without any interactions, or even logistic regression can handle interaction terms, right? So you would be able actually to infer logistic regression model that would be as good as the black box classifier.
Yes.
So your answer is yes?
So it's not that good. I mean, you basically get.
Great, but then we could just use logistic regression classifiers.
So would we arrive at the same result?
Well, I'm not sure.
Yeah, me neither.
You're saying the most important parameter.
Yeah.
Fine. So you wouldn't explain all the variation.
You have beta values there in the graph, right? I mean, the problem is that the model is richer. You're just simplifying the model, right?
Yes.
To get the explanation. Okay.
I mean, that's basically the point, to make people understand, you know, because basically almost everyone understands graph. There are newspapers, this kind of graphs.
Actually, I was not following you from the beginning. I'm sorry about that. Maybe
Okay.
you explained this, but from this, what I understood so far, usually this in the industry is done with decision trees. So you usually build decision tree to describe some black box model, and this is well-known technique and works for a while. So maybe just briefly, what is the difference between your approach and decision tree?
Well, basically, for this approach, we can chuck any classifier into it, and we get a proven, robust solution that is basically uniform across all of them. You know, there's no fiddling with parameters. With decision trees, you always have the issue of pruning, plotting. If it's very large, it's, again, difficult to understand. That's why, basically, the decision tree is a very good model, just for that reason that you said. That's why I put it on the slides. You know.
Okay.
Okay.
Okay, is there another question?
It's okay. That is, you can actually use the
Yes. You could use the variables you get from the neural network in the logistic regression, I guess. And that would be a nice methodological way to find good variables to use in logistic way. That would be just my add to the issue
correct.
before, yes. Because I've been using random forest, which uses the same contributions, and the results are very good.
Great.
You can never find such good combinations by hand or manually. So.
Interesting.
This is how machine learning was usually done. It's a great way. I did it that way as well. What we're doing with like in the next lecture with deep mining and artificial networks and so on, all of this is replaced by a big black box, and so you lose something, but you also gain something, because when you target the data, when you pre-process the data, when you transform and stuff like this, you always make some decisions. And it's like your human decisions. You can make mistakes. You can lose some data. So by replacing it with a big black box, you sort of hope that the black box would do that thing better. So then you hope that things would level out. So I'm Peter. I have a shirt, but actually I'm a geek. I used to be Linux kernel developer and stuff like this. Okay. Yeah, okay. And I'm going to talk about deep learning. Now, it was said that, you know, I would explain everything in deep learning and give you, like, you know, a hands-on introduction and everything, but it's impossible in half an hour. And last time that I announced, or when we discussed, approximately half of people said that they're not too familiar with deep learning yet. So what we'll do is, like, we'll quickly go through and figure out what deep learning actually is. So we all know about this Go competition in Korea a few weeks ago. There was a similar competition 17, 18, 19 years ago with Deep Blue in chess. And at that time they said, okay, so people were a little bit disappointed because the chess computer was not intelligent. It was just like, you know, algorithmic power. And then they said, yeah, but, you know, computer will never learn to play Go. Okay, so they did it. And then they said they'll never learn to understand language and speech and recognize objects in pictures and so on. So they said never. A few years ago, when I got interested in this deep learning, because I was actually a machine learner and neural networks were not something that you'd want to keep away from that. Microsoft came with this particular chart and said this is the error rate on speech recognition, and you know it was leveled for about 10 years, and then after 10 years they made like really good progress. Now notice that this is actually, it's a logarithmic scale. So they went from something like 20% down to 7% or something like this. And actually, ever since 2010, they've been improving speech recognition with deep learning by approximately 18% every year. It's a competition in object recognition. That was back in 2010, and the error rate was 27%. They got a little bit better, and these blue dots are normal computer vision program algorithms. So in 2012, there was like a deep learning algorithm, and they went down to, I think, 16, 17%. In 2013, there was just one normal computer vision algorithm. All the others were machine learning or were deep learning. And in 2014, they actually went to 7%. Do you know what's the error rate that humans can do on this particular data set? Let me tell you a little bit about the data set. They took ImageNet. There's 14 million images in 20,000 categories. They took 1,000 categories. And the point is that, like, you see an image and you have to classify what it could be. So, and the classes would be like, you know, all the possible dog breeds and, you know, all the possible lizard breeds and stuff like this. So Andrei Karpathy, who's a doctorate student, I think, on Stanford, actually took time and trained himself on this particular case, okay? And if the computer accuracy there was 7% error rate, he got 5.1% error rate. So he was better, okay? But actually that thing was in 2014. So now we're actually a little bit better. So you might be wondering what deep learning actually is, okay? I already mentioned that there was something neural networks and things like this. So 10 years ago, it was like totally heretic to think about neural networks. Now they're kind of popular again. So let's have a look what neural networks are. So these are neural networks, and this is not what we're going to talk about, because that's actually natural neural networks. We're talking about artificial neural networks, which are very much different. And please don't do this sort of like, you should distinguish this thing. It's not the same thing. So it's an old idea. They made the first neural network computer back in 1957 with these vacuum bulbs and stuff like this, and it actually worked. And then from 1957, not much has actually changed for about 50 years, like a few little things. So this is a model of artificial neuron. It's got some inputs, and it produces an output. And what it does is actually it does logistic regression. So you may be familiar with linear regression. The point is like you get some points, and you need to find a line that would go through these points with the minimum error, so that all the points would be the minimum distance. And you get, like, you know, you make like a line equation, which is m y mx plus c, or like the other one would be ax plus by plus c equals 0, okay? And then if you change this equals 0 to inequalities, either bigger or lower than 0, then what you would get is not 0 here, but like here would be negative values, on the other side there would be positive values, and that's actually, it's a logistic regression. Pretty much the same thing, except that this time you're trying to like split the plane in two sides and get, like, you know, positive samples and negative samples on each side itself. So that's pretty much what a neuron does, okay? So this is like ax plus by plus c times 1, okay? You sum it up, and you get a result, which would be, for example, so here are actually like 3 inputs plus a constant. On this case, it was actually 2 inputs, like x and y. But then the result actually is the same. Like you get a plane that would like split. You could imagine like in the 3rd dimension or something like this. This would be like a plane that would be like positive here and negative here. So all that a neuron does is actually, it's a mathematical equation of a line of this, like, you know, the thing that you all know from probably secondary school. It's nothing more, okay? We just draw it this way because, I don't know, because it's more sexy. Like you get newspapers to hear to listen to, and so. So what about if you want to do a regression where it's not just a line, okay? Okay, so let's hope that like we could split this line into several segments and then fit several these regressions. And then what we do is like, you know, we repeat these regressions, these neurons, and we get like one for each segment, okay? The only problem is that what we started was just a line. It was linear. So if you sum up several lines, you still get a line, okay? You want to kind of like for the line to be a little bit nonlinear in some places. So what you do is actually, after you sum up those lines and those planes, or like those inputs, you provide some nonlinearity. Okay, so when you cross the 0, you don't just do a line, but you do something to make it a little bit different. Okay, so this is like the one that we spoke before. If you do something like this, then you can actually say, okay, so now this one neuron will do one part, and depending on when you place them and so on, they can then model any particular line. So you can, if you have enough neurons, you can then sort of model any line or any equation or anything like this with just this logistic or linear regressions. Okay, are we following? Yeah. Okay. So then you can do this. Okay, and it's nothing more. It's really just like the first layer. This is what you do with this. And then what you can do is, okay, then you should just rinse and repeat, and hopefully if you do enough layers and so on, you should like solve your homework or drive a car or something like this. That's the major idea, okay? So here's also like how it could drive a car, like it needs to get some input. So this would be, for example, these input neurons. Let's say that these neurons on the input would be connected somehow to pixels, or like, you know, to imaginarily it would be like to cells on the retina, but it's just like pixel activations, and then you feed these pixel activations to the first level of the neural network. And here's an example, a very common data set, MNIST. It's actually 28 by 28 matrices with all possible digits that were scanned from checks. Like, it was still in the time where people were like writing checks, and they tried to learn how to recognize digits from checks. So you have like 28 by 28. You just like make a line out of this. So that would be like 28 by 28. It's like something like 760, and you provide like 760 neurons on this side, and supposedly 10 neurons on this side if you want to learn how to train to recognize images. And if you just do this, like several layers and so on, you go to above 90% accuracy. So when you train these networks, I'll actually, if you give me time, I'll show you. Can we see? Yeah. Okay. Perfect. It's an example how like a neural network would kind of like learn. It doesn't really learn. It just tries to fit to that particular line or to that input data. On the input level, you kind of like set up the input combinations. On the output level, you set up the output combinations, and then you try to squeeze and set up those weights here, so that like after a while, after many repetitions, the network would learn itself how to repeat your input data. And the point here is like the way that they try to paint this thing is they said, okay, red lines would be weights that are negative, green lines would be weights that are positive. If it's like really thick, then it's a big weight. So this would be like a big negative weight. This would be a small negative weight, and so on. These weights would be like somewhere between minus some small number and plus some small number. Like on this case, the input neurons would be like 0 and 1 and 0, and then you have like this neuron then would be activated 0.01, this one would 0.015, 0.71, something like this. And then you propagate it upwards, and it should kind of like provide the result that you're searching for. So there's like two steps. One is inference, which is you provide the input data, and your weights are fixed. So you set up the input data, and in each step, like you kind of like promote this information to the next level. So you would say 1, and you multiply by something, and you add those nonlinearity, and you get something. And then you just repeat until you get to the end. But at the inference level, you don't change the weights. Okay? When you train, when you kind of like when you train the network, then what you do is you fix these current values, and you change weights so that you get like that your results would be would fit the one that you want. Okay, when I showed you those like lines, you know that like you can fit any line to any points if you think of it that it's multiple equations with multiple variables, and if you have enough variables and so on, then you can fit that. The point is that if you want to go many and many layers, then those equations would become very long and very complex. But you could theoretically still do it. So what you do instead is like you just train, instead of like do a full setup of the network, you just say, okay, like these weights should be more into this direction, but I'm not going to set them specifically just to this particular input case. I will always like change them just like by like 1%. And then if I repeat this thing with all inputs for 100 times, then slowly it will converge to where I want them to be. Okay. So that's the main idea. And then the other thing is that the deeper that you go, more complex models you'll be able to learn. Okay. So the premise there was, okay, so the more layers, the more better, yeah? Except that from 1957 to about 2007, it didn't work that way. So as you went across like 4 or 7 layers, things started becoming like really, really nonlinear, and they started oscillating and things like that. It was just like an old TV, you know. It would work, and then you would move for like 10 centimeters, and it wouldn't work anymore. And actually, for a long time, then it was a lot of discussion about how cool those neural networks and stuff are. But in reality, there was not much to show, and there was a lot of philosophizing and a lot of words. And actually, the whole artificial intelligence community at that time split. And they say, okay, this would be the artificial intelligence guys, and all the proper normal guys who knew mathematics say we're not any more artificial intelligence, we're machine learners. And as machine learners, we do mathematics stuff, we can show them, we can prove them, and it's repeatable, okay? And the whole thing went so far that at approximately after like 2000, it was really, really difficult to get any paper with the word neural networks accepted to any science conference or something like this. It was just as if, like, you know, if now I was a physicist and I wanted to apply with a paper on cold fusion on physics conference. It's like no go. It was banned. Okay. So there's just and also like they cut their funds. So it's just like a few small institutes that were still having like a few people funded to do research, but eventually they did some progress. Okay, and these are actually the 4 people: Jan LeCun, Joshua Bengio, Jeff Hinton, and Andrew Ng, who were kind of like keeping the whole thing alive. And then after like 2005, 2007, they figured out how to solve these things. So, and then the other thing is that they couldn't get any papers accepted with artificial neural networks, so they invented this new term called deep learning. Okay, that's the reason why we're talking in deep learning. That's pretty much it. And let me spend like 1 minute on just a thing, which is when you do machine learning, when you take some raw data from nature and so on, usually there's some structure in that data. Like even if you ask a person to say a random number, okay, it's been proven that it's very likely that the random number that somebody will give you is going to be a prime number. So it's not random, it's a prime, you know? It's kind of like, if you ask anybody, give me a random between 1 and 20, they'll say, okay, 17. Yeah? It feels like a little bit weirder. So if we take a really weird photo, okay, which would be like, let's say, the surface of Mars, what could be weirder than that? Okay, it's still pretty familiar, and there's a lot of structure, a lot of like, it's not really random, because like random would be something like this. That's random. Okay, that's not random. It's far from random. And most of stuff in the real life and so on is not random. It's got structure. So I've shown you these digits. They're very far from random. Okay, they're like in terms of pixels. There's black pixels and white pixels and some gray pixels on the edges and so on, and the white pixels are connected together and things like this. So very often you will want to use this fact that the world is actually simpler than pure randomness, and this is something that deep learners have started working on. So this thing that I'm showing here, that's the main idea of deep learning back in 2000 something, 2005, 2007, which is if I take those numbers, those digits, like 740 pixels for each digit, okay, maybe I should be able to encode those digits into less information, okay? So maybe in 50 or something like this. So this is like 700 pixels. This is 50 neurons, okay? And then maybe, okay, maybe I should be able to restore that original information. I should be able to learn how to restore that original information from just those 50, because there's a lot of regularity. Just think of if I had a JPEG algorithm, I could compress that JPEG because there's regularities, and then I could decompress. Okay, so here you encode that data, and here you decode that data back into the original. And the way what you do is now you have like a 2-layer neural network. Okay, you show it digits on the input. It should generate some output, and then I should like feed the original input image back to the output. Okay, and if there's enough regularity and so on, then this particular network should be able to restore the original image back to where it was. It would be very difficult for that random image, but it would be easier for Mars image, or it should be even easier for those digits image. So then what you do is once you've trained it how to sort of encode into more abstract space, you just throw away this last layer, and you take these things as output. Okay. Next thing that you do is you just like repeat the whole process again, except that this time you don't work with the original images anymore, but you kind of like encode the output of the previous layer and try to restore it. And then what you get is like here, this is a little bit more abstract. This should be even more abstract. And then you rinse and repeat. Okay, you get the idea. Do you get the idea? Yeah, it's not so complex. So you could also think of it in this way. I'm putting these input neurons. I'm encoding everything. I get just like a few neurons in the middle, but the information there should be like very abstract. Okay, and then I'm decoding it, and I should get the original input neurons again. Okay, now think that what would happen if we did this on that particular MNIST digits data set. So we put here 700 input pixels, okay? And we should restore 700 input pixels. But in the middle, we just leave 2 pixels, or like 2 neurons activations. Now these neuron activations should be like between 0 and 1, or -1 and 1. It depends on your nonlinearity. So technically, you should be able to encode every input combination of pixels, not just number 1 and 2 and 7 and so on, but every specific image into these 2 neurons, which would then, like, you could put them on a plane. Like, one would be the x coordinate, the other one would be the y coordinate, and all the pictures would be represented by points on this like 1 and 1 plane. So that's actually what happens. Okay, it will encode those numbers into these planes, and each specific pixel would then be able to kind of on a little bit more abstract level encode the information about that particular image, like whether one was straight or sided, and how the 3 and 5 and things like this were done. Okay, so that's what we did. And what we did in this case was actually, how this image was generated was we didn't really take this whole input plane, but we just like scrapped the whole input part of the network, and then we made a for loop with x's and y's, and did the activations of these pixels, and then plotted the reconstructed images. You get it? Okay. So an interesting thing then would be like, okay, but what about this neuron or this neuron? Or what about if I just like fully activate this neuron? Because the idea here is that, like, it would start with pixels, and then it would kind of like build some abstract features, and then more abstract, and so on. So let's have a look. This is actually for the same data set. On top, there's just small little segments of those images. Here on the second level, there are a little bit more complex segments. Here they're even a little bit, and here it's almost close to those images. Okay. So the whole point here with this deep learning is actually you don't have to provide a lot of input data. It should be able to infer itself how to build more abstract components out of which it should be able to kind of like figure out what it's dealing with. And the other thing is, for all of this algorithm, we didn't use any label data. We just used the total unlabeled data. We used those input images and output images. It could be pieces of Mars pictures, or it could be letters, or it could be music notes, or something like this. It should be able to learn and restore. Okay. Huh? I don't know. Actually, I just took the. So that's what they did on Google. They used millions of screenshots from YouTube videos. And they built a huge, huge neural network with, I think it was something like 10,000 computers. And they were training it for several days. Okay? And they were hoping that the network would be able to learn more and more complex features by itself without actually saying it what it is about. So then they tried, and they kind of like activated one neuron, and they figured out what that neuron represents. And we see that, like, the first, that neuron represents a diagonal line. And then there was one neuron that would kind of like fire when there was a face. And there was one neuron that would fire when there was a cat. And this is all unsupervised. Like, the neural network learned it by itself. So as, like, remember that last slide or that slide from the previous presentation, that's what is normally machine learning. It's kind of like you will take the data, you will clean it up, you will get some feature extractions, like if it's computer vision, SIFT used to be really good. And then you would do a classifier like an SVM, and you would produce some output. And with deep learning, you actually provided input, and then you hope that the network would kind of like encode and figure out those features by itself and produce good outputs. And it would also learn how to kind of like level up where to actually use those neurons, where these neurons are used in the best possible manner. So if we go to this particular data set, they kept going on. This is 2014. The last results actually that I got, and this is about 7%, 7 and something. The last result is a few weeks old, and they got it to a 3.08%. So they're much better now than humans at this particular task. And the interesting thing then is this is like before deep learning. In 2012, they started with 8-layer neural network for image recognition. Okay. In 2014, they were at 19 layers. In 2014 again, I guess, yeah, they were at 22. Now, Microsoft has an architecture with 152 layers of those neurons, of those stuff that I've shown before. And the interesting thing that happened is they made it without any autoencoders. So the point is that the whole field of deep learning had actually nowadays learned how to actually train those deep neural networks without the use of autoencoders. You just like feed it more and more data, and it will learn better and better. And it may even produce better results than the ones with autoencoders. So these are like some of the stuff. I can't really go very deeply into what's in there, but some of those things like batch normalization, like deep residual network is the stuff that Microsoft did. Batch normalization, highway networks, and so on. These are all stuff that's like probably less than 1 year old, or about 1 year old. So it's really evolving very rapidly. And then the other thing is this, the GPUs. So there was this industry of graphic processors that were aimed for gamers. And it turns out that if you do a lot of gaming, your whole this 3D space where all these monsters and stuff are kind of like described by triangles and points in the three-dimensional space. So then when you do a transformation and when you move around and stuff like this, you take those lists of those like vectors and you multiply them by like 3x3 or 4x4 matrices. So the GPUs are very good at matrix multiplication, but they used to be very good at matrix multiplication with small matrices. For gaming, small is good enough. Then they figured out that hey, if we have enough like these like multiplier units in a GPU, so just as an example, I have like one of these NVIDIAs. It's not a professional one; it's the gamer one. But what it does is it has like 2,880 processors on this particular chip. And all of these processors are running at 1.1 gigahertz. So that means that you do like 3 billion multiplications and additions per second. No, trillions, yeah. So it's in teraflops now. And the point is that when you want to do this propagation, okay, you see, this is a neuron. It's, I say, I don't know, maybe it's 10 of them here. It should get sum up the activations of 10 previous neurons and multiply them by all these weights. So that means 10 multiplications and additions for these neurons, and 10 and 10 and 10. So that means if it's like a 10 by 10 fully connected layer, then that's 100 multiplications. Now, a common thing nowadays in natural language processing is that you have these layers that would be 1,000 neurons wide. So 1,000 neurons is 1 million multiplications for each inference propagation. It's pretty big. So it does help then, you know, and the other thing is like you want to do it like several million times because you're working on big data sets and so then it actually does help you have like, you know, teraflops of computing power. Because you will go, you know, you may go hundreds of layers deep and things like this. So yeah, so the point is that at a certain point then these GPU manufacturers figured out that, hey, there's a business in actually using those multipliers in doing large matrix multiplications, not just the 3x3 and 4x4 matrices, but million by million. And now they've actually started working on figuring out how to optimize their silicon to do this even better. So they're going like really, really fast. They said that this year they should be about 10 times faster than the previous generation. So it does help a lot. And I was thinking I'm now out of time. How's my time? Yeah. So I couldn't go really, really deep into explaining, you know, how everything works and all these frameworks and so. Things are more accessible than one would think of. You know, even if just thinking that, you know, I thought how neurons were really, really complicated, but then you figure out it's just a logistic regression, and like you know, you just add up and sum up lots of these logistic regressions. And even when you actually start working with that and programming, it's easier, I would say, than you would have thought. While at the same time, I think it's similar to like this, like radio amateurs, people who would make like, you know, radio transistors and stuff like this, and transmitters and receivers years ago. You kind of like when you work and train and do like and explore these networks, you also learn how they actually work, because some things are not just as obvious as one would thought of. Now, as I said, I couldn't go into details. I thought that this would be an okay introductory lecture. If there would be a lot of interest, we could actually go into more specific areas and maybe even do I don't know, share enough information that it would be possible for anyone to do like a neural network course on Udacity or something like this. That's sort of stuff to discuss for the next times. And questions?
I would like to ask you a practical question. If you are building these networks,
yeah,
I find the biggest obstacle is to collect the large enough data set.
Yeah.
So, do you know? Can you share any tricks how you augment the data, or how you compose the data set big enough?
Okay. Yeah.
Some specific problem you have.
Yeah. So the stuff that I was showing was advertising. Now that's the real stuff. Once you do deep learning, your data is not big enough. Okay. Ideally, you want gigabytes and terabytes of data, if at all possible. So there's stuff. For example, a lot of information is what you can do with images. Is you know, if you do image mining and stuff like this, you can do various sorts of crops and flips and transformations on those images. That kind of works. I also did some experimenting with neural language, natural language processing, with some sentiment analysis. And the case was that the data was, in that case, was not big enough, at least like the labeled part of the data that I had. So the interesting thing is that in those particular cases, SVM was actually better than machine learning. And I do have like even like, some articles would say, yeah, once you cross, if you want to do proper machine learning, you should have more than millions of examples. And the point is that usually it's really easy to make this neural network a little bit too big. And then when the neural network is too big, it will kind of not sort of learn from that particular structure of the data. It's big enough to actually, it may be big enough to actually memorize your whole input data. So I don't know, I was working something on faces, and it turned out that like, if there was just a couple thousand faces, maybe 10,000 and so on, it could be easier for the neural network to, rather than actually figure out where the features and what the smile is and so on, learn what the background around the face was, because there was more information there. And then like, when reconstructing, it learned from that thing. So yeah, that's the pain, which is if you work on deep learning, it's great to have a big data, or you need to be very inventive about how to augment, or not really augment, but how to pre-process the data to kind of like multiply it and cut away stuff that you think would hinder learning.
This one, I would like to continue the discussion with our panelists. So, before we keep it here, I would like to invite Blaž, who is the professor at Faculty of Information Science in Ljubljana. And Belak is chief analyst at Goopti. So if you have any more questions, let's ask our panelists, and we'll see different opinions. Why deep learning might be a good idea or not. Okay, and one more question.
Reading the articles, I came to the conclusion that most of these state-of-the-art models are they came to these results empirically. So I suspect that it is really hard to compete against big group of researchers with your own PCs, and because what I want to ask is there any analytical explanation, for example, how do you choose the kernel size, the number of kernels in each layer, and so on? Because I suspect that we don't have this knowledge.
So usually, like, you make the model as big as it fits in your GPU. It's as simple as that, and then hope it doesn't overfit, and you'll do all those tricks. So yeah, I agree. I think that what a lot of this whole machine learning community is doing now is actually they're kind of like manual genetic algorithms when they're kind of putting together various architectures of how you set up your neurons and neural networks, like topologies. The other thing, though, is that many of these interesting networks and topologies and so on, you will get them online with the topology including all the weights. So for example, VGG, the 22-layer one, or like the Google's Inception, which is 50-something layer ones, it's actually like 200 megabyte file with all the weights and everything. You can sort of use this so you don't have to train your network for like several weeks of time. You take that thing as like, the basic features for the first layers, you cut at some point, and then you train your own stuff over there. I think I think also that there's a lot of low-hanging fruit in what can nowadays be done, even with the with the current knowledge and the networks and so on, in terms of if you're sort of more interested in the applicability side. Scientifically, yes. Pretty much all of those 4 guys and all of the, most of the computer scientists that were actually working in the academia in the past are now employed at Google, Facebook, Baidu, Microsoft, and these big companies. And it's not just because there's bigger salaries there, but it's just these companies have both big data sets and big data centers where you can actually do experiments. So yeah, there's a lot of effort on figuring out how to make these neural networks also work on smaller data set. How to do? There's a lot of talk about these probabilistic models in neural networks where you could use some of the Gaussian and stuff to train networks a little bit differently.
Okay. I have another question. I would like to ask Blaž. What is the main difference between deep learning and traditional machine learning? What are the main advantages or disadvantages compared to what we used to do, or we still do with traditional approaches?
So I don't know whether Peter has said, but so deep learning is not new, right? So LeCun wrote a paper in 1988 on convolutional networks, and it's the same technology. It's like the same stuff, right? So it was not something that was invented now, right? So the difference is, of course, the data, right, and the processing power. So what's the difference between? I think, other than that, I don't know. It's the same, right? I mean, machine learning is all about finding patterns, right? So you have some data, you try to find the patterns. You would like not to remember the data, right? But to actually find the pattern so that you can generalize over the new data. And that's exactly the same in the deep learning, right? So I don't feel that there's much difference there, right? The major, so what is happening now is that what I like actually here with the deep learning is that, okay, so this knowledge that you learn, right, the different layers is transferable, right? So you can learn the digits. Like this is the data that was Peter was showing up there. It's a famous data set from LeCun, 28 by 28, and I don't know how many. I think 30,000 of them or something. And you can actually train the network, and then you can go to the letters, right? And you can take the first few layers, and then you're going to learn the letters faster because the features will be the lines, actually. And it's not only logistic regression, but in convolutional neural networks, you have different layers. Sometimes you try to just, I don't know, go to several parts of the image and maybe connect a neuron to that part, or you would like to rotate something, or so there's this art, right? But I went away. So the answer is, it's all the same, right? It's just like it's a more complex model that, but the principles behind, I think I may be wrong, right? Because I'm a bit old now, so I mean I see like the development in this area for 20 years, and it's all the principles are the same, really. I mean, like take logistic regression. That was one of the first machine learning models ever to be used, right? It's now every neuron is logistic regression. So I don't know. Just the power, right? It's like big data and so on. It's just the power.
So your opinion that the breakthrough in neural networks can be attributed to increased computational power?
Yeah,
and
sure.
The amount of data?
Yeah, yeah.
How about LSTMs? They're like a newer technology, and they're a special kind of recurrent software. So what about LSTMs? They're like a new technology which are like a special kind of recurrent neural network,
They're not actually new technology. Jürgen Schmidhuber from Switzerland invented them back in mid-90s. 97, yeah. So, yeah, so I would say that that most of these concepts and so on were actually like known well before. Like, I used to work at JSI at the Artificial Intelligence Lab with Ivan Bratko at that time, and I was very disappointed. I was interested in neural networks, but it was just sort of one of the things that should hopefully work, but it didn't. So the point is that yes, it's now the computational power is bigger, and these few ideas, for example, the autoencoders and new ways of training that actually made them actually work and scale. So yes, LSTMs is one of those methods of what also works, but also like LSTM was too complex, too computationally demanding for it to actually work years ago.
Any other question?
Looking through some papers and looking for some good code on internet, it seems there are two kinds of neural networks. One is convolutional neural networks for image recognition, and the other is LSTM for, let's say, speech recognition or some, yes. And mainly these two are used now. Are there some good examples out of image recognition and let's say speech recognition or LSTM of using deep learning?
You mean practical examples?
Yes, practical. I can imagine that some financial data should be useful, but it's not published.
Mm-hmm. So all of this speech-to-text stuff nowadays on mobile phones and so is using convolutional neural networks. Google is now in the process of switching its Google Translate to deep learning, also convolutional networks. At one point in time, they just figured out that these deep learning methods work much better than statistical machine translation that they've been using before.
We have another practical example.
Yeah, on a less larger of a scale right now, but we're currently using LSTM in production to forecast demand, which then allows us to basically hedge our risks and set prices, and works reasonably well.
What is reasonably
well? Well, we manage to usually predict about the occupancy of each of our vans to within one seat of how many will be. There are some cases which are rather pathological, and if something happens outside of our control, we can't respond to that fast enough. This is still an ongoing area where I want to improve what we're doing, but otherwise, as the time of departure nears, we're also more and more confident into what our predictions say in terms of how many passengers will actually be. And we have a pretty decent model starting with at about 21 days before departure, and just sort of gets refined. Because we also have a problem that's quite nicely suited to various forms of recurrent networks in that we're constantly having a stream of data and new information as people buy more or less the same routes in the same time, so we get more and more information, and we obviously want models which can then take advantage of gaining this new information and also incorporate the information about the time, so basically what's the lag between separate orders on the same route and stuff like that.
I have a question. So there was this issue, what was the size of the data set, right? So what's your size of the data set here?
Our real data set is about 500,000, but then what we do is we generate a synthetic data set based on that. So we're quite aggressive in regularization, so this gives us a bit more robustness. Then we do a combination of bootstrapping, and for some things we build distributions and then sample from those. Some of it we just do bootstrapping from actual data, and then some we use distributions and sample for those to build a synthetic data set.
So I think that this is one of the limiting factor currently, right, with the deep learning. I mean, there was, I think you stated before, right? And of course, if you can, so like Go, right? Okay, you can produce as many data sets as you want to because you have a simulator, and then if you have a computer playing against each other, right, that goes, I don't know, to infinity, right? I don't know, so with Christian has been pushing me on deep learning for years now. I've been telling him wrongly, right? He was right, right? Wrongly, that this is not going to go anywhere. But this is probably because of my mindset, right? That they're not, so, I mean, because many of you come from the industry and these small companies that are in Slovenia, and so the question is how many data sets do we have, right? So we all hear about Google and Facebook, and cool, right? But there's not a single company like that in Europe, right? So what is like, I mean, are we speaking about the tail here, right, of the applications, or are we talking about something that's going to emerge, you know, and every problem in the world will be solved by the deep learning? Because I thought that this was the title of this meetup, right? Is this the technology that's going to solve everything? So in preparation for this meetup, I have a lab at University of Ljubljana, about 15 people. So I gathered, I think, at least 5 of them to talk on this, right? And I said, okay, when is going to happen? So when we're going to have machine learning that's going to know everything, right? It's, okay, if I have a small problem, I'm going to have a pre-trained neural network, deep network, right? That I'm going to expose my, I don't know, 50 cases from oncology, right? Mm. And so at the end, the conclusion was in 50 years, right? And but of course, somebody said, right, if you ask anybody, right, on any prediction, right, when humans going to be in Mars, when we're going to have the faster than travel of the light, right, and so on, it's going to be 50 years, right? Usually, I mean, we always answer 50 years because that's beyond my life, right? Well, maybe, right? So I didn't get the answer like 25 years or 20. So maybe, can I hear from you? I mean, do you agree that when this particular technology, right? So now it plays Go, right? Okay, Go is, but I cannot use it for chess immediately, right? And it recognizes the images, but I cannot use it to play music, right? So when is it going to happen that we're going to transfer the knowledge, like not stay in the same domain, but just go, you know, use the same model, right? That we're going to train on everything else, but to, I don't know, predict the value of the stock, let's say. So when is that going to happen? When computers will be actually smarter than us, right? So the answer I got from my lab is 50 years, which is like from zero to infinity, to infinity. But
well, first of all, I think that neural networks such as Peter was showing, which are more or less homogeneous, aren't a long-term viable solution. That even now, if you look at the architecture of AlphaGo or even just something like LSTM, what's happening is that you get additional complications into the deepness. Also, when you posed the question of what actually means, what's a deep learning architecture, I think that even if you look at the more classical machine learning algorithms, if you will, what's happening is that we have something which is becoming more and more akin to a deep architecture. If you look at the various Kaggle solutions, which are one of the few cases where you have a more or less real life data set and you also see the solution, what's happening is that people are more and more composing different algorithms, which in fact is also what deep network is doing. So I think that the fundamental thing that we're going to take out from this is, first of all, just the value of deep architectures or ensemble algorithms, if you want to call them, or whatever. And the second one is just the hype and the marketing push that's now happening around deep learning. But I think those two are what's fundamentally going to change. And I don't see architecture's homogeneous neural network to be the be-all, end-all solution in 20 years or in 50 years. So that's just from the perspective of technology. In terms of how your core question, the more philosophical one, when are we going to achieve a more or less general learning algorithms? If I can, I would say that in about late 2030s.
I would say no way. Can we vote on this? I mean, I'm just curious. Right? So let's say in 10 years, right? We have university intelligence. Who's for? You? Okay, 20. 20. Okay. 30. 40? 50? So it's like the median would be 35. Or, no, the median would be 30, but the average would be 35 based on what I get here. I don't know.
So I'm totally with Blaž on this one. Like I breathe with you. I was always harassed by Christian about deep learning and so on, and me being a machine learner and so on was like, no way. That's neural networks. You don't do that. What I find interesting is that if you look at the whole machine learning or artificial intelligence, whatever, I would say that these connectionists, which is the people who did neural networks, is just one area. Like, then there's symbolists and there's people who do with probabilistic models and things like this. What I find interesting is that these things are not diverging, but in some cases they're converging. So an interesting thing nowadays is deep reinforcement learning, which is like one combination. The other thing is deep adversarial networks, which is the idea here is like that you make a network that generates, say, counterfeit money, and then you have another network that would be able to distinguish between real money and the counterfeit money. And as these two networks, get better, then the one that's generating money is getting better and better. And this is one thing that lets you also, in some cases, work on smaller data sets. So I think for deep learning, the big steps ahead is actually make it work also on smaller models. I think there are some ideas, lots of people are working on that, and I also agree that a nice thing is that lots of those things are transferable. But I wouldn't comment on AGI, and so it's I'm an optimist actually. Yeah.
I just want to riff off on something that Blaž said, and in the context of our future forecasting. I think one very important piece of the puzzle, which hasn't been given enough importance yet, is simulations. I think that this is like the second thing that is going to enable a vastly larger array of usages for such architectures is having readily available simulations of various physical phenomena, which will then allow us to solve the problem of not having enough data. As long as we're going to be limited by our ability to actually acquire real-world data, this is going to become more and more of a bottleneck. Right now, it may seem with all the big data hype and so forth that we're drowning in data, but actually I think it's already, the reverse is happening, and it's going to be more and more profound. So in any situation where you can either translate your problem to something where you can generate data, or even better, I think that once we're going to have various services which will simulate any real-world phenomena, this is where we'll actually see the full potential and full impact of any form of AI. And I think that, especially in my prediction, I said it's late, when I said in 20 years' time that we're going to have a full AGI, I think this is heavily predicated on, first of all, having a very strong and simulation technology available.
Getting to the right architecture, right? We solved the problem of feature extraction, which is where we spend most of the time until recently, and now the real problem is, okay, I know that the neural network will work, but I don't know the architecture, right? So the question is, do you foresee automatization of this empiricism? Could you imagine that those steps could be automated through maybe a different algorithm? To paint it differently, in biosciences, you have a machine that does all the experiments and figures out what to do and what works, what not. Here, could you imagine algorithms that would automatically build the architecture, try out new stuff with, I don't know, again, applying genetics algorithms to build the architecture or something to basically get rid of that step that has replaced the feature extraction?
So that's basically called meta-learning, okay? And there were, I'm not too familiar with this topic, but I've been following it as an informed user, let's say, for years. And there have been, I think there was a project called Metal, like in 15 years ago, that was basically not succeeding in that, right? Because it's not only a problem of deep learning and architectures, it's also a problem of any parameters for any learning technique, right? But I think there have been recent successes in that field, right? The problem is, of course, because that's another layer of the learning, right? You need even more data. So with that, I agree with Simon, right? You would need a simulator, right? Which is, I don't know, probably that reflects my age, right? Which is a bit scary, right? Because, so you basically would need to simulate people at the end, right? And then people would not be needed anymore for these machines. Well, okay, maybe I went too far, but I mean, it's true, right? So, I mean, even more data, right? But maybe just a fast anecdote, or maybe not, it's not an anecdote, but it's a real story. So there was Kaggle, it was, how many of you know Kaggle? Okay, Kaggle is a platform for competitions in machine learning, and one of them, I think last year, in about this time, was on image analysis of the plankton species. I think there were around 200 different plankton species, and you would need to base from the image, and I think there were, I don't know how many, 10,000 images, so not enough, right? So what, and I had a team from my lab, there were two guys, so one of them is actually with Jure Bontar is now with LeCun. He's been visiting back and forth, been working with him for now 2 years. So he knows deep learning well, right? He was using, so they were burning this power that my lab obviously has the GPU workstations, right? And then the hope was they would win, right? Or maybe they would get second or third. And I think that for the third there was $25,000, and for the second was, I think for the first one was $75,000. And it's a good money, right? And a lot of teams actually competed there, right? And at a certain stage they were third, right? So they were working overnight. And so for me, a disappointment at that stage was all they were doing, right? They were thinking about how to generate more data, right? What to do with the images. So they were rotating them, they were shrinking them, all these kinds of transformation to get more data, right? And then they were also experimenting with different architectures. And the way they did it was that one was working on, so Jure had his own deep learning software, and Tomasz Kočevar had his, was using some of the stuff that is readily available, right? And they merged, and this is how they got to the third place, right? And at the end, right, Jure left for New York and didn't have any time, and so they sort of, the heat was off for the last 5 days, and they finished on the 13th place, right? Not getting any money, right? And they were sad, and they said, and now they know what the first guy did. So they invented a special layer, right? A special transfer function, how to compute from, I don't know, neurons in the 16th layer to the neurons on the 17th layer, right? And so this is sort of, I don't know. Are we really into that? I mean, it's not general, right? It's how you tweak, how, so the margin of, I mean, the difference in error was not great, right? But it tells me, okay, we usually like great ideas, right? That often work, right? But it told me, right? So the lesson I got, right, looking at them for several months, was that the tweaking really mattered. I don't know if I'm excited about that. So.
Is there any known usage of reinforcement learning outside the area of robotics? For example, have there been any problems reshaped so that they could be solved using reinforcement learning?
So it's pretty new. I would say the interesting stuff here is actually like robotics is it's difficult to simulate. So the research now on this deep reinforcement learning was this Atari simulations, the games. I don't think that they've actually like put it very much into sort of. I haven't seen it elsewhere yet.
Okay, at this point I would like to thank the panelists. Yes, I would suggest that we move the questions to the debate over the snacks. Before we conclude this data science session, I would like to ask, are there any wishes or ideas what to present next time? Who is next? Do we have the next speaker?